All right, so we want to take a quick look at the binomial distribution and binomial probability experiments. So a couple different things that we need to happen in order to use this. Two conditions that have to be true. Number one, there are two outcomes, success and fail. So there are only two different things that can happen. You either get what you're looking for or get what you want, or you don't. We define the probability of a success as P. So this would be P. The probability of a success, of a failure as Q. All right, so two outcomes only. There's a name for these, and it's called Bernoulli trials. Two outcomes and two outcomes only. Outcomes must be independent of one another, meaning that when you run a trial, the outcome of that trial cannot affect the outcome of the next trial. To give you an example, shooting free throws, for instance. You either make or miss, so they are Bernoulli trials. There are only two outcomes, a success is a make. Making my first free throw cannot affect the probability that I make or miss the second free throw. And so whether that's true in this particular scenario, I don't know. But if they're independent, then making or missing the first free throw does not affect the probability that I make or miss the second free throw. The binomial distribution is defined by two parameters. The probability of success, that's P, and we already talked about that. And then this is the important one, a set number of trials. So within this probability experiment, you're going to say, hey, I'm going to run a set number of trials. We're going to randomly select a set number of people and measure a particular characteristic about those people. But there is a set number of trials that we're running, and we're going to look for a particular number of successes, which we define as X. We're going to look for a particular number of successes within that set number of trials. All right, we'll do a couple examples here. Hopefully that'll clarify things for you in a minute. So here are your variables, P and N and X. In order to calculate a particular probability, we can follow this expression here. So what this is called a combination. We're looking for all of the different ways that a particular scenario can play out, or all of the different ways that we can arrange particular objects without regard to order. All right, so combinations, the formula, if you need the formula, is actually n factorial over x factorial times n minus x factorial. If you need that, you can calculate the number of ways something can happen. Or arrangements or combinations without regard to order. All right, so that's what this, and this is pronounced n choose x. So we have n particular objects, and we're going to choose those objects. Oops. We're going to choose x objects out of those n. These are just defined as we said above. So we're going to take the probability and raise it to however many successes we want, and then we're going to multiply that by the probability of a failure raised to the difference between however many objects we have or trials we're running and the number of successes. All right, so let's take a look at a couple different things that we want to be able to do. Number one, how many successful surgeries can we expect to choose? This is called expected value. So within a particular number of trials, we should be able to calculate, hey, we're expecting this many successes to happen. And that is actually the mean of our discrete random variable. That's the mean number of successes that we're looking to find. You might also see it expressed as E of X, or this stands for expected value. So the way that we calculate that with the binomial probability distribution is we just take the number of trials, so in this case 12, and we multiply it by the probability of a success. So in this particular case, we would have 12 times 0.6, and that would give us 7.2 expected successful surgeries out of 12. Obviously, depending on how many trials you run or how many patients you randomly select, that expected number of successes is going to change. So the mean of this particular distribution we can just calculate using n times p. We always figure out where the center of a particular distribution is, and the next question is always how spread out it is. And with spread, we're talking about standard deviation. So in order to calculate the standard deviation, it's kind of a long derivation, so we're not going to get into specifics about this. But all we really have to do, it's a pretty easy calculation. We need to take the square root of the number of trials times the probability of success times the probability of a failure in order to figure out the standard deviation. So for this particular example, the number of trials is 12, probability of success is 0.6, and the probability of a failure is 0.4. So let's pull out my calculator here. We want 12 times 0.6 times 0.4, and we're going to take the square root of that. That gives us 5.411 for the standard deviation. All right, so we now know where this thing's centered and how spread out it is. So now let's get into a couple specific calculations. So the first one, what's the probability that exactly 3, and you'll see why this is important in a second, exactly 3 out of 12 had successful surgery. So what we want to know is the probability that X equals 3 successful surgeries in this particular case. And the way that we calculate this is, the nice thing is we don't have to use this nasty formula in order to calculate the probability. There's actually a calculator function, and that's what we're going to use. So this is a binomial distribution, and in this particular case, we're looking at calculating a particular probability. So we're going to use the binom PDF function. What you need to specify for this particular thing is n, the number of trials, p, the probability of a success, and lastly, we want to know how many successes we're looking to calculate the probability of out of 12. So this is what I need from you. This is what I need you to specify. It is binom PDF because we want to know the probability of an exact amount, singular amount of successes. So we use the PDF function in order to calculate the probability of an exact singular amount of successes. So let's check this out. Remember, we want 3 successes out of 12 trials, and the probability of success is 0.6. All right, so let's go find our distribution function. Our function is under distribution right here, just where we found that normal distribution before. So second vars, and it's actually near the bottom. So if we just scroll up one, that'll take us to the very bottom. Remember, we want binom PDF because we want to calculate the particular probability, or the probability of a particular number of successes. So specify that binom PDF, and again, some of your calculators may be a little bit different, but again, these are the 3 things that I need. So number of trials is 12, probability of success is 0.6, and the X value is the number of successes that we're looking to calculate the probability of. So I enter my information, plug it in there, binom PDF of 12, 0.6, 3, and I get 1.246%. So this is what I would want to see from you guys as far as work goes. what did it say? 45, 1.246. And that's it. So there's your answer. Very unlikely, 1.246% of the time, in fact, that you're going to get exactly 3 out of 12 successful surgeries. So let's look at a different type of question, still dealing with the binomial distribution. In this particular case, we want the probability that our number of successes is less than 5. All right, so think about this for a second. If we want the probability that we get less than 5 out of 12, well, we actually need to calculate a bunch of different things. The first one is the probability of 0, because that falls in that interval less than 5. We also want to include the probability of 1 success, and 2 successes, and 3 successes, and 4 successes, not all the way up to 5. We want just under 5, and because this is discrete, you can't have a half a success, so we're going to stop at 4. These are all of the different probabilities we need to include in order to answer this particular question. So we could go do binomial PDF of 0 and binomial PDF of 1 and 2 and 3 and 4 and then add those together. Remember, that's that or addition rule. So we want the probability of 0 or 1 or 2 or 3 or 4. But the nice thing about the calculator is it actually has a function called the binomial cumulative distribution function. And this function is going to calculate the cumulative probability, and this is the important part, from the left or from the lower values. And so what it's going to do is once we specify where we want it to stop, it's going to work its way from the lowest, meaning 0, up to 1 and 2, and it's going to add these together and calculate the cumulative probability until you tell it to stop. So for this particular one, we want from 0 to 4, so we would go binomial CDF because we want more than 1 probability. And we're still going to plug in the same stuff. So we still have 12 trials. The probability of success is still 0.6. And then we're going to specify where we want it to stop as it works its way up from the left. So we want it to stop at 4. And that's what we're going to plug in. So let's go look at our calculator here. Here's the distribution. We want binomial CDF in this case because we're calculating the probability of more than 1 particular outcome. 12 trials, probability of success is 0.6, and then our x value is 4. And again, because this is CDF, you're specifying where you want it to stop. It's going to work its way up from the lowest particular outcomes up to 4. So you want it to calculate 0 to 4. That's what we're specifying. In this particular case, you've got a 5.73% chance. That if you randomly select 12 patients, you're going to have less than 5 successes. All right, so we're done there. Next type is more than 7. And here's where it gets a little bit tricky. So hopefully you've got a good grasp. More than 7 means 7 or 8 or 9 or 10 or 11 or 12. Or means add all of these together. The problem with this is we know it's going to be a binomial CDF, and we also know that binomial CDF calculates from the left up to whatever point you specify. So if I calculate this binomial CDF, I've got 12 trials, 0.6 is the probability of success. If I calculate up to 12, then that's going to include 0, 1, 2, 3, 4, 5, and 6 as well. So this particular function is going to include all of this. I only want this much. So what do I need to do? I actually need to subtract out all of these probabilities. I need to subtract out all of these, and I do that by taking binomial CDF. That's going to calculate the probability of everything up to the point that I specify. So it's going to be 12.6. And I want to exclude up to 6. So I'm going to specify that. So I go to my calculator. I take my go to my binomial distribution. We want the cumulative function, and we wanted to calculate up to 12. So that's the whole thing. So I've got 12.6, and I want all 12 successes. You know what? This wasn't right. Yes, it was. We're good. So calculate all 12 successes. Press enter, get that probability. That's going to be 1. And then I can subtract that from Binomial CDF. Up to 6. So 12.6, and then I only want 6 successes in this particular case. So that'll plug that in there. I've got 1 minus that particular probability, and I get 66.5%. That's the probability that I get 7 or more. We could also, if you saw on the calculator, we could also just do the complement of this. We know if we calculate this and we want everything else, we could just do 1 minus Binomial CDF. All right, if you have any questions, make sure you ask, and we'll see you tomorrow.